Brian Nakamura as a co-organizer. It's also the Ph.D. defense. So the first 48 minutes is a public presentation. Then everybody will be asked to leave and the committee stay for a few more minutes. In the unlikely event that Brian will pass, we're going to take him out to a different restaurant than the usual one. It's called Indochine on George Street, 371 George Street. But if you want to join us, you're welcome to, but you must let us know before exactly whether you're coming or not. Because last time we got yelled at, there were more people we didn't know. So I'm going to write down. But everybody is welcome to come. Right.
Thank you. And just kind of a warning to the audience, I have a little bit of a lingering cough from kind of the sinuses and such. So might be a couple interruptions in the talk. But so what's that?
Is it contagious?
I don't think so. All right, so I'll start off with some basic definitions. So the main object of study will be permutations, and I'll consider permutations in one-line notation. First, I start off by defining this reduction. So if I have k distinct integers, or they don't have to be integers, but k distinct numbers, the reduction of that finite sequence is the relabeling such that I take the smallest entry, I label it 1. I take the next smallest entry, I label it 2, and so on. And so just as an example, if I take the reduction of the sequence 63915, the smallest entry is a 1, so that stays a 1. The next smallest entry is a 3, so that becomes a 2. The next smallest is a 5, that becomes a 3, and so on. The 9 is the largest, that becomes a 5. So in a sense, it takes any sequence of distinct numbers and maps it down to a corresponding permutation. And basically, any two sequences that map down to the same thing, have the same reduction, are also called order isomorphic, which I might kind of occasionally say. Then now we'll look at classical pattern occurrences. So given a pattern tau of length k, generally the patterns will be permutations as well. Given a pattern tau, we say that a permutation pi contains tau if you can find some subsequence of k entries in the permutation that reduce down to tau, right? That are order isomorphic to tau. One thing to note is that the entries in the permutation don't need to be consecutive terms. I need to be able to find k terms that are order isomorphic to the pattern tau. So another example. If the pattern tau is 1, 2, 3, then the permutation 5, 4, 3, 2, 1 has no occurrences of tau. Right? So there's no increases at all in that permutation. Whereas the permutation 4, 2, 1, 3, 5 has 2 occurrences of the pattern tau. Namely, the 2, 3, 5 form a 1, 2, 3 pattern, and also the 1, 3, 5 forms another 1, 2, 3 pattern. Just some background. So the area of permutation patterns kind of gained interest after some early results in sorting. And in particular, one of the sort of the main early results that generated interest was by Knuth, that a permutation is stack sortable if and only if it avoids the pattern 2, 3, 1. And so stack sortable here means that you have a data structure called a stack, which is a first in, last out data structure. And if you run a permutation through a stack, one stack just once, it's possible to sort that permutation if it avoids the pattern 2, 3, 1, if and only if. And so while some people in the field of permutation patterns have continued studying sort of sorting questions, for example, what permutations can you sort?
Maybe explain very briefly what stack sortable is? Or say so-called stack sortable.
Yeah, so basically, if you have a stack, so if you have a data structure, a stack, and you have a permutation, you read off entries of the permutation one by one, and stick it into the stack, and you can, pop it off as necessary, but basically you can only read through your permutation once, and you want to, on the other side, come out with a sorted permutation. So it's, if you're able to sort it with a stack. So this, this won't be the emphasis at all of my talk. So if you don't, if that doesn't make any sense, it won't affect the rest of the talk at all. But basically, this naturally also leads to enumerative questions. For example, so you might ask, how many permutations can you sort, right, with different sort of data structures? So I make that more precise. So given a pattern tau, I define Sn tau to be the number of length n permutations that avoid the pattern tau, right? So the classical pattern tau. So again, the Sn tau denotes, so basically how many permutations out of Sn avoid tau. And then it's natural to ask, what can you say about this? So you imagine tau, this pattern, to be a fixed property in a sense. And then you have a sequence in n that you care about. Some previous results. So for length 3 patterns, these are known. Technically, there are 3 factorial possible patterns, right? 6 patterns. But there are some basic trivial equivalences for some of them. So you can reduce it down to really just the 1, 2, 3 and the 1, 3, 2 as sort of 2 representatives. Right? But it turns out that for the avoidance case, these are also equivalent. And so basically, the sequence enumerating permutations that avoid 1, 2, 3 and 1, 3, 2 are both counted by the Catalan numbers in this case. And so this isn't a trivial equivalence, but there are kind of many proofs on that. For the length 4 case, basically you have 4 factorial possible patterns, permutations, but there's only 3 classes to really consider. There are some by trivial equivalences, some by more complicated equivalences, but ultimately it's just 3, in a sense, pattern classes to consider. The first one, 1, 2, 3, 4 is known, so there's a closed form known for that. The generating function is known. The second one, 1, 3, 4, 2 is also known. So there's also a closed form for this. The generating function for this is also known. Then the very last one, 1, 3, 2, 4. So this is the one that's been kind of notoriously difficult to enumerate for. So there's no good way to enumerate these, the sequence, to generate the sequence. There's no precise asymptotics known for how the sequence grows. There's kind of a rough upper bound and a lower bound for how the sequence grows, but there's kind of a large gap. And I think every sort of method for generating the sequence is some sort of recursive type approach. So I believe the best, the sequence is only known for maybe the first 25 or 26 terms. So the best approach only generates 25 or 26 terms for this pattern. And basically, so this pattern, just to emphasize the difficulty of this pattern, there's an annual permutation patterns conference. And in 2005, the plenary speaker made the following conjecture, that not even God knows the 1,000th term of this sequence by our very own Albert. This conjecture remains open and is often quoted. And so just the general outline for the rest of the talk, I'm going to consider 2 kind of variations to this permutation pattern problem. The first is I want to enumerate permutations with exactly R copies of a classical pattern. So in the case that R is equal to 0, that specializes the classical avoidance case that was just discussed. But I'm interested in also non-zero R values as well. And so I'll present, give a rough outline for a functional equations approach. I'll also show how kind of an existing approach for one pattern can actually be extended via computers. And then in the end, I'll also briefly discuss another special variation of patterns called consecutive patterns. So I'll start off first with the functional equations approach. So first, just to generalize the definition from before, I now define for a given pattern tau and a non-negative integer r, S and tau r will be the number of length n permutations with r copies of tau. Right? So here you can imagine tau, and tau is some fixed pattern, r is some fixed non-negative integer, right? And then I'm looking at the sequence Sn tau r, right, ranging over the n values. And so again, if r is equal to 0, this is exactly what we were discussing before. So now in the case that r is strictly larger than 0, 1, 2, most of the work has focused on just length 3 patterns. So the generating function is known for some small r values for the pattern 1, 3, 2, as well as 1, 2, 3. And so our goal will be to, for some fixed pattern tau and a fixed r value, right, to be able to compute these things quickly. Right? So in a sense, it's an efficient enumeration algorithm for computing this sequence. And just for the purposes of the talk, the pattern I'll look at will be 1, 2, 3. But in general, the same work extends to increasing any length increasing pattern. So like 1, 2, 3, 4, 1, 2, 3, 4, 5, and so on. This portion of the talk is a joint work with Zalberger. So just to give an idea of how it's, just to give an idea of how the enumeration algorithm works, for any given permutation pi, I'm going to create a weight function. And so I'm going to have variables t and catalytic variables x1 through xn. And the weight of pi will be the number of permutations, sorry, the number of patterns, 1, 2, 3, or I'll sometimes refer to it as ABC, just for the purpose of notational convenience. But basically, t to the number of occurrences of 1, 2, 3, right? Times these xi catalytic variables. And these xi variables keep track of 1, 2 occurrences, occurrences of the pattern 1, 2, where the first term is exactly equal to I. And so this is going to be, for each pi, this is going to be some sort of expression in t and the xi's. And then for each n, I can create this sort of multivariate polynomial Pn, which is just the sum of the weight, basically applying the weight function to all the permutations of length n, summing them together. So just to give an example of this weight function, so for example, the weight of 2, 1, 3, 4. So this will be, so t squared, so I have 2 occurrences of the pattern 1, 2, 3, the 2, 3, 4, and the 1, 3, 4. The x1 squared means that I have 2 occurrences of the pattern 1, 2 that begin with the actual number 1, namely the 1, 3, and the 1, 4. x2 squared means I have 2 occurrences of 1, 2 beginning with number 2, right? So the 2, 3, and the 2, 4. Likewise with the x3. And one thing to note is if I set all these catalytic variables xi equal to 1, then this portion disappears out of the weight function. So the weight, it's just the weighted enumeration of the number of occurrences I have of 1, 2, 3. And then when I add this together, when these are set equal to 1, this just ends up being a polynomial in t, where the coefficient of t to the r is exactly how many length n permutations you have with r copies. So, so this weight function, in a sense, you complicate what you want, but then somehow that helps you more quickly compute what you want. So, without going into great detail, in a previous paper by Noonan and Zalberger, for that specific polynomial Pn, they derived this functional equation. And essentially, this functional equation says if the permutation you're considering begins with the term I, then this is sort of the weighted sum of that. And then the I ranges from 1 to n. Right? So the I represents the starting term of the permutation. And you can kind of finagle this functional equation out. And then the goal is to be able to use this functional equation to quickly compute this thing. One thing to note is that you don't have, for any given n, you don't have to symbolically compute this gigantic multivariate polynomial. In a sense, you can take this expression, push it through the functional equation to get some objects just with t and 1s and t's in here, and then kind of keep iterating that sort of process to kind of quickly compute this thing. In addition to that, it's possible to apply other computational methods to quickly compute the coefficients that you want. So namely, so the coefficients of this thing, t to the r, is exactly the term I want. So it's possible to do that. And with some of those computational tricks, you can actually reduce the method down to being a polynomial time algorithm in n. It will depend, the degree of the polynomial will depend on r, but you're viewing r as some fixed sort of predetermined value. And so everything has been implemented in Maple. For example, the r equals 0 case. Again, this is just the avoidance case, which is counted by the Catalan numbers. R equals 1 case. You can quickly compute some values here. And so technically the first 10 terms you can compute with brute force, so that's not very impressive. So just to kind of skip ahead a little bit, if you want r equals 6, you can easily compute the first 20 terms. And here is the 15th to the 20th term. So, brute force, you wouldn't be able to get up to 20, for example, the 20 factorial permutations. So now some extensions to this approach. So that approach was specifically for the pattern 1, 2, 3, but it can be extended to any increasing pattern. So 1, 2 up until k. That specific work is joint with Zauberger, along with the computational methods. And so, for example, if I wanted the pattern 1, 2, 3, 4, one occurrence of that, then here's the 60th term of the sequence. It can be computed via Maple. Likewise, you can also extend it to patterns of the form 1, 3, 2, 1, 2, 4, 3, and more generally, increasing patterns where the last two terms are transposed. And so, for example, so if I wanted the first 60 terms for one occurrence of 1, 2, 4, 3, I can easily do that too. And just as a comment, so for each specific pattern, that ugly, complicated weight function I defined earlier, those differ depending on the pattern. And depending on how you define the weight function, then the functional equation changes. So in a sense, there's many possible ways you can define such a weight function, but you have to define the weight function in such a way that you can actually extract the functional equation from it in the end. So it's easy to define, arbitrarily define weight functions, but the hard part is finding some weight function where you can extract a functional equation from it to use that to quickly generate terms.
Did you compute anything for r equals 0 in this particular case?
This one?
Yeah, the increasing pattern.
Yeah, so yeah, that I have done, so that's also known too.
Yeah, there's a well-known upper bound when r is 0 in this particular case. Did this match with the known result on that?
So it definitely matches with what's known. So there is a explicit formula for the 1, 2, 3, 4 avoiding permutations.
The increasing one.
Yeah, done by Gessel. So yeah, there's a generating function known for that one, as well as a kind of a closed form formula for computing it. Yeah, so it does match.
R equals 0.
R equals 0.
Yeah, that's
the upper bound, the least upper bound.
Yeah, but nothing has been known so far. Y equals 1.
Okay. I just thought that if his method matched with the known thing for r equals 0 as well.
Yeah, good question. Yes.
Yeah. So yes, so I do not get different results that are already established, which is good for a thesis. In addition to that, it's possible to also combine known functional equations to consider multiple patterns simultaneously. So for example, if I want to count permutations with 1 copy of this pattern and 3 copies of this pattern, right? It's easy to kind of merge the functional equations to do so, if you already have functional equations in this sort of sense. And then one last thing is you can also refine by this permutation statistic called the inversion number. Basically, the inversion number is the number of 2-1 patterns within the permutation. So it kind of represents how unsorted the permutation is. But it's easy to kind of quickly refine by inversions as well. Now, some additional extensions to the approach is, So that previous approach can be generalized to handle other patterns if you consider more complicated catalytic variables, kind of the double subscript xij catalytic variables. So in a sense, as opposed to having n catalytic variables, now you have something on the order of n squared catalytic variables. So in terms of runtime, this sort of really slows down the runtime, but it still goes beyond sort of the direct approach, and we can also still squeeze out some interesting information. So some additional patterns that you can handle is with this more general approach. First is the patterns 231, 2341, and more generally the increasing 2 through k followed by 1 pattern. The one nice additional extension you can get with this approach is actually the pattern 1324, which even for the avoidance case was the very, very difficult one. I cannot get 1,000 terms, but the approach does generate some interesting results. So just
I equals 1, how far can you go?
Not very far. It's like under 20 terms.
Oh yeah, but more than 10.
But more than 10.
R equals 0?
So basically, I'll mention kind of outlines of the approach, but I get up to around 23 terms. The record is 25, 26. So just to kind of show a little bit of the setup, I won't go into full detail, but I'll have 2 sets of catalytic variables now, xij and yij. Like the I and j being flipped, that's not a typo. For notational convenience, I'll store the variables in kind of like a matrix of variables, say xn, and likewise for yn. And that's just for notational cleanliness or convenience. The idea is that originally I was going to show the weight function that I wanted to use, but it kept shooting off the edge of the slide, so I figured it wasn't worthwhile to show it. But basically, you define some weight function, then you sum over those weights to get this polynomial again, Pn. And you want it done in such a way that if you set these matrices x and yn to the all ones matrices, then it collapses down to a polynomial in T again, and the T to the rth coefficient is what you want. And so with the right choice of the weight function and such, you can derive this you can derive a functional equation that looks like this. And here, the R1, R2 are some matrix operators. Basically, they take n by n matrices and spit out n minus 1 by n minus 1 matrices. So basically, it's some matrix operator of, there's some row deletions and adding together columns and scaling some columns kind of thing. But you can get this sort of functional equation. Now, in the case that r equals 0, right, where there's still a lot of questions, you can specialize the functional equation and sort of find some shortcuts to kind of make the computations more quick. And so, in particular, this allows us to compute the first 23 terms of the sequence. So the record is maybe 25 or 26 terms, and that was by a paper done maybe less than 10 years ago. The previous record before that, just a few years prior, was 20 terms. So this kind of falls in the middle. And also, I should mention, too, that...
And you only use macro, it is very slow.
Right. And actually, the issue here actually is it's not as much a runtime issue. It's that since I have sort of order of n squared catalytic variables, it's actually a memory issue. Basically, when I try to run for 24, it runs out of memory. But for 23 terms, it finds it in under an hour of computational time. And then, yeah, for 24, it runs out of memory. So it's primarily a memory issue. The one final nice thing about this specific approach, though, compared to maybe the previous approaches, is that it's easy to refine by the number of inversions for this approach. This is useful because for the past couple of years, there's been a conjecture regarding 1, 3, 2, 4 avoiding permutations and the inversions. And basically, if this conjecture is true, then it lowers the asymptotic upper bound for the sequence of 1, 3, 2, 4 avoiding permutations. And so basically, this approach can get much, much further in terms of the computational data relevant to that conjecture. So all the data I can get definitely still empirically verifies the conjecture. So that's one more thing. Now I'll switch a little bit. And the next thing I'll discuss is taking an existing approach and then using computers to kind of extend it or get kind of more results. So in this particular case, I'm going to consider generating functions. So in the previous portion, I just cared about enumerating the sequence, right? Kind of efficiently enumerating the sequence. In this portion, I'm going to actually find the generating function. So I define the generating function. So given a pattern tau and some fixed non-negative integer r, this is the fr is the generating function for that specific sequence. And one more thing that I'll utilize for this portion is the fact that dict paths are counted by the Catalan numbers. So recall that dict paths are lattice paths with up steps, down steps. They start at height 0, end at height 0, and also never go below the x-axis. Right? And so the number of dict paths of length 2n are counted by the nth Catalan number. So that would be relevant in this portion. And also relevant is the generating function for the Catalan number. I'll denote c of x, or most of the time I'll just write c. But the c represents the generating function for the Catalan numbers. And so this particular portion will focus specifically on the pattern 312. So this is equivalent to the pattern 132, but for the purposes of the methods here, looking at it as 312 is more convenient. And basically, so Fulmech, maybe 10 or 15 years ago or so, gave an approach for computing the generating functions for small r, right, for r equals 1 and r equals 2. He also did the same thing for the pattern 321 for r equals 1 and r equals 2. But that's, in his paper, that's all he did. So our goal is to try to extend this approach by computerizing what he did. And so just the general idea for his approach, so I'm just going to really outline his approach and then mention certain parts that can be automated. But the general idea for his approach is that I take the relevant permutations I want to count, then I map them into this sort of generalized dict path, which is a dict path that also permits downward jumps. So in addition to the upward step, the down step, there's also straight down jumps allowed in the path.
Vertical.
Vertical, yeah. But still the other same rules apply. It has to start at height 0, and at height 0 can't go below the x-axis. And the idea then is to count the relevant paths instead of actual permutations. So the mapping he shows is an injective mapping, and basically the downward jumps will actually kind of mark occurrences of the pattern 312. Let's see. One additional thing to mention, so I'm actually not going to show the specific mapping from the permutation to the paths. Actually, the mapping requires you go to like an intermediate object first that he kind of refers to as a height vector. So the permutation gets mapped to some intermediate object first, and that gets translated into a path. But for the purposes of this section, I'm just going to treat this mapping from permutations to paths as almost like a black box kind of function. So just as a warning. And again, the goal is to study this approach and then show how it can be kind of made systematic and then extended using computers.
So if you allow down jumps, what's the generalization of the Catalan number? What's the sequence? The number of them.
That I'm not sure. So actually, we don't actually specifically count all such paths. We just count some